All right. Well, thanks very much for inviting me to discuss this paper, and congratulations to Bryan and co-authors. This paper is accepted at JF, so my task is a little unusual, so I'll hope to provide some sort of useful food for thought going forward. All right, so what is this paper about? So in general, it's about a high-dimensional regression problem, sort of trying to estimate this, oh, I'm pointing in the wrong direction. Trying to estimate this beta. And normally that wouldn't be a problem if sort of the dimension of the predictor set is fixed and the sample size goes to infinity, then sort of in the limit, there's sort of not too much to worry about because sort of all the estimation uncertainty can be controlled. So here, and that'll be important, sort of all the elements of ST sort of matter equally much. And sort of in this sort of high dimensional setting, you get these sort of non-standard random limits because the sample size and the number of parameters approach infinity simultaneously at the same rate. You know, the conventional approaches of learning are generally hard or infeasible there, and there's been sort of lots of ad hoc ways to sort of solve this. But sort of assume that sort of only a small subset of the predictors is actually irrelevant. And then, so if beta was sparse, then you sort of get back to the old regime by sort of saying, okay, well, it's really not that complex after all. So there's been sort of little theory on sort of how to work in this setting when sort of actually all the elements are relevant, and sort of this paper delivers much of the needed theory. Okay, so I'm going to give you some background sort of on high-dimensional problems in general. And sort of in high dimensions, sort of estimation is generally sort of a tough problem because sort of estimating a quantity sort of basically amounts to taking an average of a suitably chosen set of points. And sort of in this sort of image here, sort of as we're moving from 1 to 2 to 3 dimensions, sort of we're taking an average over the points in the gray shaded area, but sort of the sample size is kept fixed. So as you sort of get to higher dimensions, basically you end up with fewer and fewer observations in the area that you care about. And so this has been sort of characterized in the statistics literature sort of 40 years ago. Sort of Stone worked out what the optimal rates are in this setting. And sort of if you were sort of in a high dimensional setting, you sort of get this rate that sort of depends on the dimension of the predictor set. So if you were to do sort of a little back of the envelope calculation, if you want to estimate something in 11 dimensions and compare the quality with 1 dimension, you basically need to raise the sample size to a third power. So if you had sort of 1,000 observations to start out with, you need 1 billion to sort of do the same thing in 11 dimensions. So somehow the question is, why even try these problems if we know that sort of they're generally extremely hard? Well, somehow, sort of the computer scientists and machine learning community didn't read the memo, or at least thought there was a way around it, and sort of started fitting these huge models anyways, okay? So here are some examples from sort of image classification competitions, where sort of the models that sort of won these competitions were highly over-parameterized. And sort of this is one of the pictures from one of the Google presentations of ResNet 18. So in their model, sort of the training error is exactly 0. So after this point, they're just interpolating points, and sort of the training error is exactly 0. And sort of the surprising thing is that this doesn't break down out of sample, and this test error actually doesn't blow up. So if you sort of look at the sort of estimation error in general, right? So the first part here is essentially the approximation error by sort of confining yourself to a class of functions, and the second part is the estimation error. And sort of what we have is sort of that empirically, this is close to 0, right? So we're exactly fitting the points. And then sort of the key theoretical question in some sense is sort of how can this generalize by any means? And sort of that's what this paper shows sort of in the context of this market prediction problem. You can cook up even simpler settings to sort of illustrate this. So I played around with this sort of on the way here. And sort of even in sort of a one-dimensional world where you sort of have few data points but sort of a very wiggly function, and you sort of compare sort of the fit of a model that has, so this is sort of something in the order of 120 observations. And you sort of estimated 50 parameters, you get this sort of yellow curve here. And if you did sort of a random Fourier expansion like Bryan with 2000, oops, how do I go back? Oh. You sort of get this green curve. So this is sort of the outer sample picture. And sort of if you repeat this a bunch of times, prediction risk is strictly smaller for that one. So there's sort of no worry about this. So in a different setting, if you sort of did sort of a forecasting exercise like this one that we calibrated to the Stock and Watson world, so the data sort of are generated by a factor model. So the underlying structure is low dimensional. But sort of the econometrician sort of completely ignores this advice and runs sort of a linear regression anyways, using all the features that are there. And of course, you know, you can't do that sort of when you sort of have more features than observations. So you sort of just do generalized inverse rather than regular inverse. And that turns out to be equivalent to ridge regression with penalty parameter approaching 0. So this is sort of minimum norm interpolation. So in sample, we're sort of getting this exact fit of all the returns that we generated. And out of sample, we sort of get this double descent curve. So the first part here is sort of what's sort of the first descent is known. That's just bias variance straight. If you include more features, you fit the model, you fit the data better. And then eventually, as you sort of include too many, your estimation breaks down. The surprising part is the second part here, where sort of the over-parameterized model does extremely well in sort of predicting the data out of sample. Now, in this setting, and also sort of in the setting in the paper, sort of, you know, we're including more and more information in the model as we're sort of, you know, estimating more parameters. And in this example, we get actually very close to oracle risk. That is, as if we had used the true but unknown factor model underlying this simulation. All right, so the results in the paper, I mean, Bryan sort of did an excellent job, so I'm briefly just going to mention them. Sort of they characterize portfolio performance for various choices of complexity and regularization, and the investor forecasts future returns, chooses sort of this, oh my God, this pi, and then invests in the timing portfolio. And they analytically characterize the expected return, second moment, and Sharpe ratios. So those are sort of results that are not the output of computation, but they're actually analytical results, and that's quite impressive. They also analyze the correctly and specified and misspecified case, which is also very laudable. And sort of the traditional answer had always been sort of use sort of lasso or ridge or something. And sort of the answer here is that, so don't be afraid of sort of benign overfit and implicit regularization, because even sort of if you don't explicitly regularize, sort of the ridgeless solution here is pretty much as good as all the others in sort of when complexity is high. All right, so here are some thoughts. So in the current setting, sort of all the predictors are equally useful, and that's sort of also how I calibrated sort of my simulations. And the question is sort of, you know, in practice, and the authors are quite aware of this and fairly explicit about this, well, probably we don't know, right? So what if some aren't very useful, and sort of how should we generally approach the problem? So I played around with this a little bit, and sort of in this Stock and Watson calibration, so what if the first 50 are only relevant? It turns out that there's sort of not much loss. You don't get quite as closely to oracle risk, and sort of back here I'm basically just adding noise, and this is sort of getting a little wiggly. The same thing basically happens when only 100 features out of those 500 are relevant, and we're still sort of getting this beautiful double descent curve. So I'm suspecting, but this is sort of has to be shown more explicitly, that sort of this phenomenon of high complexity probably applies more generally than sort of what's stated here. Now here's what happens if sort of only 10% of the features were relevant, okay? And there's now no ordering to sort of where the relevant features sort of pop up in the data. So here you can start out sort of fairly poorly, and then sort of estimation will anyways break down as you approach the interpolation threshold. But surprisingly, at some point you will capture all the relevant features, and you sort of get sort of double descent again. And that sort of leads me to believe that at least in some settings, the result probably applies more broadly than what's proved in the paper. You could sort of take a sort of a more extreme view on this and say, well, what if I used only garbage, okay? So in that setting, you still get double descent, but the levels are way off. So we're nowhere near sort of oracle risk where we'd want to be. And this is sort of a metaphor that if you sort of had a sparse structure where sort of only sort of a handful of predictors mattered, then probably we'd be getting into trouble somehow. So my second comment is sort of how to choose complexity. Basically the takeaway from Bryan's presentation is choose as much complexity as you can. And sort of in the paper, there's sort of, so we don't see double descent in sharp ratios. We basically see single ascent. So it's always going up in complexity. And there's sort of some pictures in the paper that sort of suggest that at some point there might be sort of a flattening of this curve. And it'd be sort of nice to sort of characterize when this flattens out. So if you take comments 1 and 2 together, sort of in many empirical situations, we don't know exactly what to choose and sort of what's relevant or irrelevant, or how many of those are relevant or not. And sort of, the broader ask, and I know this is sort of a huge ask, is sort of can we sort of abstractly characterize situations when we should opt for high versus low complexity? And there's sort of some hints that you can sort of piece together from different parts of the literature. So for example, in the neural network literature, there's some fascinating new results that basically sort of show that neural networks work extremely well when there's sort of a low dimensional underlying structure somewhere in the data. And neural networks are sort of find this low dimensional structure extremely well. So you could have sort of a function in sort of thousands of variables, but if there's somehow a low 5-dimensional structure underlying this, you get the 5-dimensional rate. And that was sort of what was happening in my simulation, is there was a factor model underlying this all. There are also sort of results that sort of put more stringent conditions on the smoothness of the function that we're approximating. So if this function becomes sort of ever more smooth as the dimension increases, you can actually get sort of a dimensionless rate. And sort of somehow, sort of putting all these things together would be fascinating and probably provide sort of a useful guidance for sort of when to sort of opt for these models. And finally, this is sort of I know this is a big ask, but sort of in this setting, and in most of machine learning, inference is extremely challenging because we have these non-standard limits. And if we can sort of somehow outline a path to inference, I think that would be extremely useful, because I think most sort of financial economists somehow expect that. And certainly I've run into this criticism in my own work, but Bryan and Semyon are really smart, so I'm sure they'll find a way to sort of piece this together. The paper is sort of extremely well written and sort of a pleasure to read. If you've never dealt with random matrix theory, there's sort of a beautiful motivation in the paper for why this is relevant here. I think Bryan was very modest about this, but sort of forecasting sort of excess returns on a value-weighted stock market has proven to be fairly hard. So I think the empirical success is actually a bit understated. So generally, I think there's sort of lots of interesting stuff here. I know there's sort of an agenda of complexity that Bryan and Semyon with varying co-authors are pushing, which I'm looking forward to read. But overall, I think this is sort of an impressive piece of work in characterizing these results analytically rather than through computation. So that's all I have to say.